Hi, this is John Whitaker again for the Mathematical Analysis 2 class, and this is our 19th video lecture. And we're talking about series of complex numbers. Right now we're really concentrating on series of real numbers. We left off with what I call the divergence test. And I want to write that up again and remind you what we'd say to our calculus 2 students, what the divergence test is. So here's what we have. Here we say, if the sum as k runs from 1 to infinity, a sub k converges, then the limit as k goes to infinity of a sub k must be 0. We proved that last time. I called it the divergence theorem, but essentially what we say to the students is the contrapositive of this statement. We say, if the limit as k goes to infinity of a sub k is different from 0, then this series as k runs from 1 to infinity of a sub k diverges. So it's a statement written this way of a conclusion of the divergent series, and that's what we say. I wanted to clarify that. The next thing I want to talk about is something called the Dichotomy Theorem. And here's what it says. It says, let a sub k be a sequence of real numbers where a sub k is greater than or equal to 0 for all k. Then the sum as k runs from 1 to infinity of a sub k converges if and only if its sequence of partial sums forms a bounded sequence. And this is really a consequence of the theorem that we saw in the previous term. And so that particular theorem we saw in the previous term is the monotone convergence theorem. So let me write this down before I write down the proof of the dichotomy theorem. It says for the monotone convergence theorem. It says that a monotone sequence of real numbers converges if and only if it is bounded. So proof of the dichotomy theorem, we say let the ace of k's, k runs from 1 to infinity, be a sequence of real numbers with ace of k being greater than or equal to 0, then the sequence of partial sums which we'll denote by S of n, and of course that's equal to the summation, maybe as k runs from 1 to n, of the ace of k's. Okay. Is an increasing sequence. So, the sequence of partial sums is a monotone sequence. So it will converge if and only if it is bounded. Okay. Remember what it means for the series to converge. The series will converge if and only if its sequence of partial sums converges. And so the sequence of this partial sum this sequence of partial sums will converge if and only if they're bounded. So that means that this sum of the ace of k's converges if and only if its sequence of partial sums is bounded. And that ends that proof. Okay, the next theorem we want to talk about is something called the comparison test. Here's what it says. So part A, it says if the absolute value of a sub n, which will be terms of the sequence that we're adding up, are less than or equal to c sub n, and that's true for all n bigger than or equal to some n sub naught, where n sub naught is some fixed integer, and if the sum is n runs from 1 to infinity of the c sub n's converges, then the sum is n runs from 1 to infinity of the a sub n converges. Part B says if we have 0 is less than or equal to b sub n is less than or equal to c sub n, and that's true for all n greater than or equal to n sub naught, where n sub naught is some fixed integer. And the sum is n runs from 1 to infinity of the d sub n's diverges, then the sum of, I called these in my notes. Let me make it consistent with my notes. I called this last guy's a sub n. So the sum of the a sub n's as n runs from 1 to infinity diverges as well. This kind of makes sense. Here's the way that I think about it. Essentially, for part A, kind of this way. We think of this as being, in some sense, a smaller sequence than the c sub n's, and the c sub n's converge. Okay? Kind of think of it that way. And here, the d sub n's are the smaller sequence, and the d sub n's, they diverge, so they're going to push, with them being positive, they're going to push anything bigger than it to go towards infinity as they go to infinity. Okay? And so the c sub n's in this top part, since they converge and they're positive, they kind of hold anything down below it. Positive terms. There's a little bit more to what I just said. More to it than what I just said, but the part A. Okay, so here's the proofs. We'll start off with part A. And so we'll let absolute value of a sub n be less than or equal to c sub n. And that's true for all n greater than or equal to n sub naught, where n sub naught is some fixed integer. We also suppose that the sum of the c sub n's, as n runs from 1 to infinity, that converges. We want to show that the series of the a sub n's converges. That's what I want to show. Okay, what we're going to do is we're going to use this Cauchy criterion for convergent series. So here's what I'll say. We'll let epsilon be greater than 0 be given. And if there exists an integer, let's call it big N, such that for all n greater than or equal to m greater than or equal to n, the absolute value of the sum as k runs from m to n of a sub k, if that's less than epsilon, then this series, as k runs from 1 to infinity, of a sub k converges. Okay, so that's what we want to show. We've got to get this in. And that converges by the Cauchy criterion. Okay. That's what we're trying to produce. Well, since the series of the c sub k's converges, there exists an n bigger than n sub naught, so we go far enough beyond n sub naught, where, of course, n is an integer, big N. Such that for all n bigger than or equal to m, bigger than or equal to big N, the absolute value of the sum as k runs from m to n of the c sub k's will be less than epsilon. Okay, and that's by the Cauchy criteria. And we know the c sub k converge. So, since for all m bigger than or equal to this number we have n, the c sub m's are going to be greater than or equal to 0. We have that from the assumption for part A that the c sub m's after you're bigger than n sub naught, for the m's bigger than n sub naught, and that's what m's we have here. The c sub m's are going to be bigger than the absolute values of the a sub m's. We have this statement. Then, for all n greater than or equal to m greater than or equal to n, this absolute value of this sum, k runs from m to n of the c sub k's. Well, these are just positive terms. You sum up a positive term, take absolute values. That's the same thing as the sum of the positive terms. And so we know this guy's equal to this guy, and we know this guy's less than. It shouldn't be less than. It's really less than or equal to by the Cauchy criterion. So it should be equal to here, okay? I made a mistake. Less than epsilon, so we need to change that. Even in what we wanted, it should be less than or equal to the previous forward. Okay? So for all n greater than or equal to m greater than or equal to this big N we have, we look at this sum as k runs from m to n of the a sub k. Well, that's going to be less than or equal to the sum as k runs from m to n of the absolute value of the a sub k's. Here I'm using the triangle inequality. And then that's going to be less than or equal to this sum of the c sub k's, and that's less than or equal to epsilon. And so by the Cauchy criterion, that means that this sum, as k runs from 1 to infinity of a sub k, converges. Okay, for part B, we're going to let 0 be less than or equal to b sub n, be less than or equal to a sub n, for all n greater than or equal to this number, n sub naught, and we're going to let this sum, as n runs from 1 to infinity of the d sub n's, we're going to let these guys diverge. Okay. We want to show the series of the a sub n's diverges. Okay, that's what we want to do. Well, we're going to do this really by contradiction. So suppose not. Suppose this series of the a sub n's converge. Okay. So we got these a sub n's converging, and we have this inequality for all n bigger than or equal to this n sub naught. Well, that inequality from part A, so by part A, we have that, that the sum of the d sub n's, this is by part A, as n runs from 1 to infinity, that they would have to converge. But that's a contradiction because we're assuming that they diverge. Thus, this series is n runs from 1 to infinity of the ace events must diverge. And that is the proof of part B, and thus the whole theorem. Next theorem we want to look at is really known as the geometric series test for positive term series. Or non-negative. And here's what it says. It says if 0 is less than or equal to x is less than 1, then the sum is n runs from 0 up to infinity of x of n is equal to 1 over 1 minus x. It says if x is greater than or equal to 1, then this series of x of n is n runs from 0 to infinity diverges. Here's the proof. Okay. So let's start off by just supposing x is greater than or equal to 0 and x is not equal to 1. So we'll handle the case when x is equal to 1 later. So we'll just say x is not 1. Okay. Okay. Then, when we look at this sum as k runs from 0 to n of x to the k, you know, if x is equal to 0 over time, then we're just summing up a bunch of zeros here. We'll say we won't worry about 0 to the 0. Okay, that's either 0 or 1. I don't even want to find it. Let's say 1. And we'll say that's fine. But here, we'll just look at it. Look at it with I guess we'll look at it with x being greater than or equal to 0, and we'll say 0 to 0 is 1. And so here we have this, this quantity. It's going to be equal to 1 plus x. Okay? So x to the 0 we're going to say is 1. And then x to the first x plus x squared, we write it this way. X to the third plus all the way x to the k. Or x to the n, I should say. And that's what we have. Okay. Now, there's a little trick here. If we examine the sum as k runs from 0 to n of x and k minus x times the sum as k runs from 0 to n of x and k. Well, first of all, that can be rewritten if you think of the sum as just one quantity. It's really 1 minus x times that sum. So what we'll say is 1 minus x times the sum is equal to, the sum is k runs from 0 to n of x of k minus x times this sum is k runs from 0 to n of x of k. Rewriting this first. And now, I'm going to expand this. Okay, this is equal to, well, the first is going to be 1 plus x plus, we'll keep on going to x to the k. And now, I said minus this quantity. Okay, look, I'm going to take x times each one of these guys. So I'm going to get x plus x squared plus all the way up to plus x to the k plus 1. Okay, most things are going to cancel. The 1 is going to survive. Okay? In the subtraction. Also, we're going to have a minus x to the k plus 1. So, that means that this quantity, 1 minus x, times this sum, as k runs from 0 to n, of x to the n, is equal to this quantity. Thus, we have that this sum, as k runs from 0 to n, of x to the n, is equal to 1 minus x to the k plus 1, all over 1 minus x. Here, I guess this should be a k, this should be an n, and I've made some mistakes here. This should be an n, this should be an n plus 1, so let's make that change. Here, this should be an n plus 1, and here, this should be an n plus 1. Sorry about that. So those are what should change. Okay? So that's the result we get. Okay, so in this formula, if we letting n go to infinity, we get that the sum as k runs from 0 to infinity of x of k will be equal to the limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x. Okay? That's what it is. So that's provided this limit exists. So here, if we think of some kind of subcases, if you will, if 0 is less than or equal to x is less than 1, so we said x wasn't 1. So if we have this part of the cases for x, then this limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x. Okay. All right. See, the x's are fractions really close, or in between 0 and 1, if you will. And then when you start raising them to powers, they go to 0. And so this ends up being 1 over 1 minus x. And so in this case, this sum equals to 1 over 1 minus x. So I'm kind of taking the sequence of partial sums here. I've eliminated the sequence of partial sums. That's what I'm getting in this case. Now, if x is bigger than 1, so I haven't handled 1. I'm not looking at when x is equal to 1 yet. Then, the limit as n goes to infinity of 1 minus x to the n plus 1 over 1 minus x. Well, if you stick in numbers that are bigger than 1 and start raising them to powers and keep on raising them to higher and higher powers, that goes off to infinity. And so this is going to be a 1 minus form of a huge number, so that's negative numbers. Here, this is going to be negative numbers. You're going to get this goes towards infinity.
So in this case, this sum, as k runs from 0 to n of x sub k, this diverges. It diverges. Okay. The last case is if x equals to 1, then our sum, as k runs from 0 to infinity of x to the k, well, that's just going to be 1 plus 1 plus 1 plus, okay, and which diverges. The partial sums will be unbounded. That's what gives us divergence, and that concludes the proof. Okay, the next thing I want to write down is the theorem due to Cauchy, and we're going to use this theorem a little later on, but here's what it says. Kind of a strangely thought of statement, but here's what it says. It says, suppose a sub 1 is greater than or equal to a sub 2 is greater than or equal to a sub 3, which is greater than or equal to. We keep getting lower and lower and lower, but yet all the terms of the sequence are greater than or equal to 0. Then the series the sum as n runs from 1 to infinity of a sub n converges if and only if the series, okay, this is what you get to kind of compare it to. As k runs from 0 to infinity of 2 to the k, a sub 2k, well, this is, just to get an idea what this is going to be a sub 1 plus 2 times a sub 2 plus 4 times a sub 4 plus 8 times a sub 8 plus, it goes on forever like this. So, if and only if this series converges. Okay, here's the proof. Okay, so we'll let a sub 1 be greater than or equal to a sub 2, be greater than or equal to a sub 3, be greater than or equal to so forth, all the way down to everything being greater than or equal to 0. And what I'll say is that this sum, as n runs from 1 to infinity of a sub n, and this series is k runs from 0 to infinity of the 2 to the k, a sub 2 to the k, are both non-negative. Both series non-negative terms. Okay. So one thing we can use here is by the Dichotomy Theorem. these series will converge if and only if their partial sums are bounded. So here's what we observe. You let S of n equaling to a sub 1 plus a sub 2 plus all the way up to a sub n. So that's the impartial sum for the series of A. And T sub k equal to a sub 1 plus 2a sub 2 plus 4a, so 4 plus all the way up to 2k times a sub 2k, which is, of course, the k partial sum for the other series involved. Okay, for n less than 2k. Okay. All right. Now remember, S of n is written right above. So here's what I'll say. We have this S of n. I'll write it down again. It's a sub 1 plus a sub 2 plus all the way up to a sub n. Okay? We got that. Well, it's going to be less than or equal to, I'm going to write down a sub 1, then plus a sub 2 plus a sub 3, plus, and then I'll write down a grouping of a sub 4, plus a sub 5, plus a sub 6, plus a sub 7, plus, okay, we keep adding terms like this, all the way up to a sub 2k plus a sub 2 to the k, I should say, plus 1, all the way up to adding the term a sub 2k plus 1 minus 1, like that. So that's what I'm putting in. All right, and then that's going to be less than or equal to a sub 1. And now look, we're assuming that a sub, that this was a decreasing sequence. So a sub 3 got smaller. So if I replace a sub 3 by a sub 2, a sub 3 got smaller. So this is 2 times a sub 2. And then here I replace a sub 5 by a sub 4, a sub 6 by a sub 4, a sub 7 by a sub 4. That's going to be greater. And so we have plus 4 times a sub 4. Plus, we'll keep going. And so here I replace all of those guys by 2 to the k. So I'm going to have 2 to the k times a sub 2 to the k. And so this is equal to t sub k. Therefore, we have that S of n is going to be less than or equal to t sub k in this case, when the n is less than or equal to 2k. A good way of understanding this line, possibly, right here, okay, is letting n be a specific number and k being a specific number. Like, for example, letting n be 7 and k be 3. Try to see if you understand that line. Okay. Now, for n being greater than or equal to 2 to the k, we have S of n is equal to a sub 1 plus a sub 2 plus all the way up to a sub n. And what I want to tell you, that's going to be greater than or equal to, let me give it a little bit more space here. It's going to be greater than or equal to a sub 1 plus a sub 2 plus the quantities a sub 3 plus a sub 4 plus a sub 5 plus a sub 6 grouped together plus a sub 7 plus a sub 8. And still on the same line, I didn't have enough room. I'll say plus a sub 2k minus 1 plus 1. All the way up to adding up a sub 2k. Oh, that's one line. This is going to be less than or equal to 1/2 plus 1/2 a sub 1 plus a sub 2 plus 2 a sub 4 a sub 4. So really, just in this line here, I'm replacing a sub 3 by a sub 4, and a sub 4 is smaller, so this line's bigger. Plus, here I've got, it'd be 4 a sub 8 plus, and we get down to the last one, and that is plus 2 to the k minus 1, a sub 2k. That's what we get. Okay, this is equal to 1/2 t sub k. So, in this case, we get 2 times s sub n is going to be greater than or equal to t sub k. So we've got these two results. Now, remember this was an if and only a statement comparison about convergent series. So I'll start off this way. So if is sum as k runs from 0 to infinity of 2 raised to the k a sub 2 raised to the k converges. Okay, then the sequence of partial sums, p sub k, are bounded above. Okay. Say by m sub 1. Okay. Then m sub 1 is an upper bound for the sequence of partial sums for the other series, which we're calling S of n. For if not, then there exists an n sub naught that's a natural number such that f sub n sub naught will be greater than m sub 1. Okay? Now, if we pick k greater than, pick k such that 2 to the k is greater than n sub naught, okay? Then the t to the k will be greater than m, and that's a contradiction. Okay? Okay, and so this m sub 1 is the upper bound of the sequence of partial sums for the a sub k series, the series of a sub k's. And so its partial sums are bounded, and thus, since they were positive term series, that means that that this series, as n runs from 1 to infinity, of the a sub n's converges. Okay, going in the other direction, it says if the series as n runs from 1 to infinity of a sub n converges, then the sequence of partial sums S of n for that series are bounded above by some number, and here I'm going to say, it doesn't matter what we call it, I'm going to call it m sub 1 again. It's maybe different than the m sub 1 we had before, but anyway, I got it. And then I'll say then 2 m sub 1 is an upper bound for the t sub k, which are the sequence of partial sums for the other series involved. For if not, then there exists a k sub 1 such that the t sub k sub 1 will be greater than 2 times m sub 1. And so at this time we pick n greater than or equal to 2 to the k sub 1, then 2 times this s of n will be greater than t sub k sub 1, which will be greater than 2 sub m sub 1. And so in this case we have that s of n is greater than or equal to m sub 1, and that contradicts m sub 1 being a bound above for the s of n's. And so this says that this series, as k runs from 0 to infinity, 2k a sub 2k converges. And that is that proof. Okay, ladies and gentlemen, that's enough for today, and thank you very much.